Hi, welcome to part 4 of the video series Deriving R Squared. Today we are going to discuss simple linear regression in more detail and lay out the base for the main derivation. Just means that we're going to try and think of how to approach the derivation. Okay, so let's get started. The first thing we're going to do is we're going to have a small recap. We're going to go back to the example we were talking at the end of the previous video, and we're going to use that to understand the next few steps. Okay, so last time we were discussing this example, which was that let's say you went to Bombay, okay, and you had a look at a lot of houses. So now you have a lot of data with you. This means that you have the costs of all the houses. Along with that, you also have data on the number of bedrooms in each of those houses, the square foot area in each of those houses, and the floor on which each of those houses are. Okay. And what we said was that we could potentially create an equation that shows how the cost of each house is dependent on each of these three features or variables, because all these three are variables, right? And after finding that equation, we'd be able to use it for new houses. So let's talk about this sentence in a little more detail. But instead of taking three variables, what we are going to do is we are only going to use one variable. Okay, and that variable that we're going to use is square foot area. You could use any of them. For this example, I'm using square foot area. So let's say costs are some sort of a function of S or square foot area. S is the variable, and therefore is equal to ms plus c, where m denotes the slope. I've written it here too. Okay, so instead of x I've used s. It's just a change in the variable name, that's it, nothing different. And c is the constant. To be able to understand why we use m and c, please have a look at the previous few videos in the video series and it will start making a lot more sense. Okay, so we've said that this cost is dependent on square foot area, and the way we can define this dependence is using m and c. Okay, now how do we find m and c? M and c can be found using previous data, which means that all the data that you have on costs and the square foot area can be used to find the best values of m and c so as to create a good equation. Okay, now why do we need such a good equation? Why do we need this dependence of cost on this square foot area? How is it going to be useful to us? So let me give you a situation. Okay, you have all this data. Now you want to go to a new house and you see that you like that house. Now the thing is this, that any realtor or owner is going to try and give you a higher price. They are going to try that out. It's the basics. That's what everyone does. Now, for you to be able to negotiate your price down, you should have some sort of an estimate in your mind on what this house actually would cost based on the different, features it has. So let's say in this case, you're only looking at the square foot area, and based on the square foot area, you should have some sort of an estimate on the cost of that house so that you can negotiate with the owner. Now just think, let's say you did find out this value of M and C. Okay, you understood this dependence of cost on the square foot area, you have this equation with you. You'd be able to easily find the cost of this new house, because all you would have to do is to find the cost of the new house. I'm going to call it cost n, n denoting new house. Cost n is equal to m of, you already have m, you've found out m times Sn, means square foot area of the new house, plus whatever C you found out. And there you have the cost of this new house with you. This way you'll have some sort of an estimate based on the data that you have, that this should be the cost of the house, and now you're free to negotiate. Think of the advantage of being able to predict the cost of a place. Yeah? That's why we are trying to find out MNC. Because not only with costs, with so many other things, MNC or these coefficients and the constant can help you find out or predict values based on the data that you have already collected. Okay. Now let's have a look at this graph over here. Okay. 1 second. Okay. Now over here, what you'll notice is I have just drawn a few data points, which means that each of these blue color circles that you see denote the cost of a house with respect to its square foot area. I've just plotted all these points. Okay. Now think of this. So we were saying there should be a line. Mx plus c is basically the equation of a line. So we are trying to say that there is some sort of a line that goes through every single data point. But now look at this case. Is there really one straight line that can go through every one of these points? The only line I can see is a nice zigzag line like this. But can this line really be denoted by the equation of a line? If you watch the first video, you'll know that the answer is no. It cannot be denoted using mx plus c, because this zigzag line has different slopes at different points. And if you notice over here, when we say cost is equal to ms plus c, m is just 1. We just have one slope over here. That's not possible. So what do you do? What do you do in such a case where you can't even create a proper line? How will you find the equation? That's where I'm going to give you a real life example. Okay, so let's say you're with your friends or your siblings, and you have this difficult decision to make. What should all of us eat tonight? That's a very tough situation. It can lead to fights. It can lead to a lot of stuff happening. So what do you do then? In this sort of a case, what you do is, now there are 3 situations, okay? The first situation is this. You say that let 1 or 2 people compromise and let a few people have exactly what they want. Now that is also going to create a lot of havoc, because 2 people are going to be really disappointed, some are going to be happy. It's not going to be a good balance for the friendship or the siblinghood. Now think of the next situation. Nobody gets what they want. A tough situation again, because everybody is going to be unhappy then. Then comes the third situation. What if each person adjusted a little bit? Just a little bit. So everyone has to adjust a little bit, but they all get a little bit of what they want. That's an optimal situation, which means that even though everybody cannot have what they want, you could have something that's close to what everyone wants. And that's exactly what we're going to do over here. We're going to try and create a line that goes through in such a way that it is as close as possible to every one of these data points. That's what we're going to try out. Okay, so let me show you a graph. Okay. Now have a look at this graph. We've drawn a line, and if you notice, let's take an example point. Okay, let me take this one over here. Let me take a different color also. Let me take red. Okay, so let's say this is data point 1, so D1. Okay, now this D1 has some cost, right? Some sort of cost, which can be denoted by, I'm just going to write it over here, some cost Y1 and some square foot area X1. Okay, now let's see how this data point is shown on this line over here. Okay, so you see the square foot area has to stay the same. That's why if you see horizontally the data point hasn't moved, it has only moved vertically. So X1 still stays the same, but Y1 is changing. Okay, so this new one, let's call the Y value on this new point as y1 cap. I'll tell you the reason for cap a little later. Okay. So this means that D1's y value is changing. Y value is changing from y1 to y1 cap. Okay. This also means that the projection of D1 on this line, let's call this line L, on this line L leads to an error in the y value because it is going from y1 to y1 cap. Okay. So we could say that the error in the y value, so let's call it error 1 because we're talking about data point 1. Let's just keep the notation the same. So error 1 is equal to y1 minus y1 cap, and what we'll do is we'll get the modulus of this. Why? Because let's say if D1 didn't lie above the line and it lay below the line, you would get a negative value, and that does not really help us in this case because we just want to know the magnitude of the error. We don't want to really know the direction. That doesn't matter to us. So when we say y1 minus y1 cap, we take the modulus. Okay. Now in a previous video, we've also discussed why taking just the positive value can cause issues. The modulus function can lead to issues with respect to differentiability. I have not discussed this in a previous video. What I'll do is I'll put in a link to Khan Academy's video on differentiability. I would recommend watching it anytime you want to understand why we prefer not to use the modulus function. Okay. So what do we do instead now? If we want the value to be positive, this is something we saw even earlier with variance. What we do is we just square it. So we get E1 square is equal to y1 minus y1 cap, the whole square. Right? Now we have errors that are always going to be positive, whether y1 is greater than y1 cap or not. Okay. Now we found this. Now ideally what we would have wanted is that each and every error is the minimum error possible, which is technically just 0, which we saw cannot happen. So what we try to do is, our thought is this, sorry, that we try to sum up all the errors. Okay, so we try to sum up all the errors. Just one second, let me change the color. Okay, sorry, I've lost my mouse. Okay, there it is, finally. Okay, so we sum up the error values. So we sum up all the error values. What I'm going to do is, okay, so first of all, this sign that you see over here is called sigma. It denotes the summation sign. Okay, and what we'll say is we'll call this EI because we're saying for every data point from data point 1 to data point 20, we want to sum up the errors of all these data points with respect to the line L that we're creating. So you'd say I is equal to 1 to I is equal to 20. This is the notation. Okay, and we're summing up all the errors. That is what we want. And this expression of summing up all the errors together is called the sum of squared errors. Which is also called SSE. Okay, SSE is a term we're going to use a lot. It's going to be especially helpful when we come to finding R squared. So please remember this term, SSE, sum of squared errors. Okay, now how do we denote EI? Okay, before we get to EI, we have to think of this. How do we denote Y cap? What is yi cap? Basically, it's a point on this line L. L is that line which has the slope m and c. So you could say that it is the best approximation of xi, which is the square foot area, plus c. So m and c represent the slope and the constant of that line we thought could be the best line possible, the most optimal line possible. And we substitute xi over here because, as we discussed earlier, the square foot area never changes. It's only the cost or the y value that changes. Yeah. So therefore, yi is equal to mxi plus c. Yeah? This means that the error, or ei, which is equal to, so I'm going to write it without the modulus for now. Okay, y minus yi minus yi cap. Actually, let me just put the modulus here. Okay, which is equal to, what is this equal to? It's equal to yi minus mxi minus c. There. Or equivalently, ei squared is equal to yi minus mxi minus c the whole squared. So this would also mean that the sum of squared errors, okay, now let me light this in a different color. Okay, so the SSE based on our new definition is equal to the sum from I is equal to 1 to 20, or let's just say, let's not take it as 20, let's say how many ever data points are there. So let's represent the number of data points with n, or a variable n that denotes the total number of data points. Okay, wherein we're saying the actual value of y is subtracted by mxi and c, the whole squared. Okay, now we have this equation. Now what do we do with this equation? Remember what we said, we are trying to minimize this sum of squared errors. We want the errors to be as small as possible. Okay, let me write this here. We want to minimize SSE. How do we do it? Anything that comes to your mind, something we have talked about in a previous part of the same video series actually. It is the minima. I know, right? So cool. So what we are going to do in the next video is this. We're going to find the derivative, partial derivative of the sum of squared errors. So partial derivative is something I have not discussed in a previous video. I would highly recommend studying this topic before you watch the next video I create. We are going to take the partial derivative of SSE with respect to the two variables that we have, which are m and c. We need to find a good m and a good c that can give us the minimum error possible. So by finding a very good optimal m and c, we're basically trying to find the best line possible that can decrease the sum of squared errors as much as possible. We get it to its minimum possible value. Hence, we take the minima. Okay. So for example, if we were finding the derivative of the sum of squared errors with respect to m, we will try through this. We try to find the best value of m so that this equation gives us the smallest value possible. Okay, we'll talk about this in much more detail in the next video, in which we're going to mainly derive m and c, or rather find an equation that gives us the best value of m and c so as to get the smallest sum of squared errors. Okay, then that's it for today. I hope you have a great week, and I'll see you in the next video. Thank you.